Okay, shall we start? Shall we start?
Yes, sir.
Okay. So in the last class, we have discussed some of the problems which are related to the conduction, is it? So all the conduction problems were simply based on this particular equation here, which is known as Fourier law of heat transfer, which says Q is equal to, that is the rate of heat transfer is equals to minus K, which is K is the thermal conductivity value, and A is the area of cross section, dt is the temperature difference between two walls, dx is the distance between the two walls. So all the problems were based on these particular formula. So it was easy. We have solved in the last class. So few problems regarding to the conduction we have just discussed in the last class. In this class, what we'll be doing is we'll be discussing some of the problems which are related to the convection. In the model number 3, whatever you can expect the problems from conduction, convection, as well as from the radiation, and all the problems in this particular module, that is module number 3, would be of the basic level. That means the basic formula would be there, just the substitutions of some parameters and asking you to calculate some of the remaining parameters. So that is how the problems are designed for module number 3. So all the problems, that means the problems based on conduction, problems based on convection, as well as the problems based on the radiation, all have this basic level of problem solving techniques. Okay, let us see some of the problems which are related to the convection now. The rate equation for the convection heat transfer. So this is the equation which governs the convective heat transfer. The equation which governs the conduction heat transfer is minus Ka dt by dx. Do remember this expression. For the convective heat transfer, it is Ha into Ts minus Tf. Okay, that is what is Ts? Ts is nothing but the surface temperature. What is the temperature of the surface? Okay, and Tf is the temperature of a flowing fluid. Tf is the temperature of the flowing fluid, and your Ts is the temperature of the surface. So that is how it is. So the convective heat transfer is given by Newton's law of cooling. There it was the Fourier's law of heat transfer is Ha into Ts minus Tf, where H, the only parameter Q, it is the rate of heat transfer, or here it is conductive heat transfer, it has to be convective here. Okay. A is the area exposed to this heat transfer, Ts is the surface area, Tf is the fluid temperature which the fluid is flowing, and H. So do remember what do you mean by H? H is nothing but the coefficient of convective heat transfer. A long name, but you can shorten it as coefficient of heat transfer. So H is what? H is the coefficient of heat transfer. Remember this. And K is thermal conductivity of the material. See, these two parameters are totally different parameters. K governs for the conduction and H governs for the convection. To remember this, K is thermal conductivity, whereas H is coefficient of convective heat transfer, or in a shorter way, you can just say it as coefficient of heat transfer. Okay. Next. Say yes. So if you just pull out the H from this particular expression here, you might know and analyze on what all factors does the H value will depend. So H value would depend on the rate at which the heat is getting transferred. H is dependent on the area through which the heat is getting transferred, surface temperature, and the fluid temperature. So these are all the parameters on which the coefficient of convective heat transfer is dependent. So that is what it is given here. Apart from that, even the geometry of the surface is also uh, effective in determining the value of H. Okay. So in a electrical analogy, we have discussed that for an electrical circuit like this, okay, there would be some resistance, current would be flowing, and there would be a potential difference to drive this. Okay, in order to drive current through the resistor, I require a potential difference. So how should I relate these all? How should I relate? What is the relation between I, V, and R? Yes. Yes, guys. Why no one is responding, man? Are you there or what? Still in the festival mood? Reza, Mr. Nitin, Adarsh, are you there? Pratish Suvarna.
Yes, sir.
So, how do you relate the current, voltage, and the resistance in an electrical analogy? We have discussed in the last class, right? It is I is equals
V is
to
equal to I.
V by R. Is that right? I is
Yeah.
equals to V by R.
Yes, sir.
Hmm? Okay. So here, I is the amount of current flowing through the resistor. V is the potential difference which drives the current, and R is the resistance. So similarly, in a conduction, if there is a plate like this, and this temperature is T1 and this temperature is T2, okay, and I want heat to be transferred in like this. So in order to have the same sort of analogy, what I'll be doing, Q is the amount of heat transfer that is equals to the potential difference, that is the temperature difference between these two, in this case, divided by the resistance, where the resistance for the conduction and the resistance for the conduction is L divided by Ka. This is what we have learned, is it? L divided by Ka is nothing but your resistance for the conduction. Similarly, when there is a surface and there is a flowing fluid like this, okay, the flowing fluid is temperature of Tf and surface is temperature is Ts. And here also you can draw an analogy where the heat transfer, which is here conductive, and here it is convective. The conductive heat transfer is a difference. The potential difference is nothing but the difference between the surface temperature and the fluid temperature divided by R convective. So what is that R convective here is? It is 1 divided by H into A. You have to remember these two expressions. What is R for conduction? That is L divided by Ka. Similarly, for R for convection is 1 divided by Ha. Okay. The analogy of these three is just similar, man. Okay. All these three can analyze in the same way, where here you require current to be passed, here you require the heat to be passed. Okay. You require the potential difference across the ends to drive it. So V here. You require the temperature difference across the ends to drive it. So it is T1 minus T2 here and Ts minus Tf here in case of convection. The resistance to the current is known as R, which is measured in ohms, which I have written here. Here, the resistance is calculated as L divided by Ka, which is the resistance for the flow of heat, for the obstruction of heat. Okay. Same case, and this also, the resistance for the convective heat transfer, the resistance for the convective heat transfer is given as 1 divided by H. Any doubts in this particular analogy here? Understanding these three concepts? Yes.
No, sir.
Understood, everyone? Shall we move and solve some of the problems on this?
Yes, sir.
Yeah,
Yeah.
sir.
Okay. So here's a simple problem. It says a hot plate of 1 meter across 1.5 meter is maintained at. So your hot plate is something like this, 1 meter across 1.5 meter. So this is 1.5 meter, and this is 1 meter, he says. Fine. Is maintained at 300 degrees Celsius. So which temperature is this? Is this TS or TF? Which temperature is it? Should I take this particular thing, 300 degrees Celsius? So should I take it as TS or TF? Yes.
Yes.
Okay. So if I take Ts is equals to, which is maintained at 300 degrees Celsius, so your hot plate is maintained at how much? 300 degrees Celsius. Air at 20 degrees Celsius blows over the plate. So you can just change the color now. So air is blowing at a rate of what? So air temperature, that is flowing fluid temperature, is 20 degrees Celsius here. What else he has given? The convective heat transfer coefficient is 20 watt per meter square degree Celsius. So convective heat transfer, that is the value of H he has given. Calculate the rate of heat transfer. Direct substitution problem, no issues. So from the Newton's law of cooling, Q is equals to HA into Ts minus Tf. H is nothing but the convective heat transfer coefficient, which is given here. And A is the area. How you'll calculate the area? It is 1.5 into 1. So again, it is 1.5 over there. Ts, Tf, it is 320, which is the surface temperature as well as the flowing fluid temperature. Substitute it, you'll get the value of 8.4 kilowatt. Any doubts in this problem? Pretty simple, straightforward question. Should I keep this diagram which I have drawn here, or should I erase it? This one.
Keep it.
Okay. Next one. A wire of 1.5 mm diameter and 500 mm long is submerged in a water at an atmospheric pressure. The electric current is passed through the wire and is increased until the water boils at 100 degrees Celsius. Under the condition, if the convective heat transfer coefficient is so much, find how much electric power must be supplied to the wire to maintain the wire surface at 120 degrees Celsius. It is very good question here. Okay, so what he is doing, there is a bath. In this particular bath, there's a copper wire, something, which wire of 1.5 mm diameter. So I'll just draw it like this. There's a wire like this of 1.5 mm diameter. So the diameter of this is 1.5, which is already given here, and 150 mm long. So the length of this particular wire is 150 mm. Okay, surface area. So how did you calculate a surface area of a cylinder? So surface area of a cylinder is nothing but pi dl, right? Remember? Yes or no? Or it is 2 pi RL, anywhere. Anything is the same thing. Okay. So calculate that surface area, which is given as pi dl, where d is substituted in meters, you'll get it in the meter square. So surface area, you'll get it. Wire surface temperature is given as 120. Water temperature is given as 100. Convective heat transfer is given as H. Calculate the value of Q. HA Ts minus Tf. H which is already given here. A is you have just calculated, which is the surface area. And Ts minus Tf. Ts is here, Tf is here. Substitute. So the total convective loss is nothing but 63.6. So this much amount of heat you need to supply through an electric source. Clear? Any doubts in that?
No, sir.
Hello?
No, sir.
Any doubts in this problem, guys? Both are very simple, but the only thing is the additional what you have learned is calculating the surface area. That's it. Any doubts here? Any doubts?
No, sir.
Okay. So such a simple basic level of problems that we asked both from conduction and convection. We shall see the radiation. For me, out of conduction and convection, radiation is more interesting. The problems are good here. So for that, a few laws of radiation you need to analyze before you go to that. Um, have you heard about this Wien's law? I'll be explaining what is Wien's law. Uh, have you heard about this Wien's law anywhere prior? There are three laws which governs the law radiations laws, which is Wien's law, Kirchhoff's law, and Stephen Boltzmann's law. So out of all these three laws, what have you heard of? Have you heard of Kirchhoff's law? Have you heard of Stephen Boltzmann's law? Anyone?
All three, sir.
Kirchhoff's law.
Kirchhoff's law you have heard. Fine. Next. Anyone Wien's law and Stephen Boltzmann's law?
Stephen's, sir,
Stephen,
Stephen's
yes,
Boltzmann.
Stephen Boltzmann's law is a very popular one. Very popular. Even the Wien's law is also, even it was there in your second piece also. Okay. The Wien's law is a little bit complicated to understand. It is also called as Wien's displacement law. Okay, hope he's given that. No, he's not given that. Okay, so why it is called as Wien's displacement law? I'll just try to explain it. What it states is, it states that the wavelength lambda to the suffix m, that is, wavelength corresponding to the maximum energy. So if your body is emitting a maximum energy, what is the wavelength of that particular thing? So that is your lambda m. Okay, that is your lambda m. That is always inversely proportional to the absolute temperature T of the hot body. So that is a simple law. So lambda m is proportional to is inversely proportional to the temperature of that particular body. What is the simple law stated here is, if there is a hot body at certain temperature and it emits a wavelength, there will be numerous radiation which is emitting by this particular body, is it? So you have to choose a wave where the maximum energy is being emitted. So I guess this to be this wave. So if I take this to be this wave, what is the corresponding lambda m for this? So this lambda m will always be inversely proportional to the value of the temperature. Got it? So that is your Wien's law. Got it? Gautam, Reza, Niharika.
Yes, sir.
Yes, sir.
So the wavelength which is corresponding to the maximum energy is always inversely proportional to the absolute temperature of which the body holds. So that is the law. And if you take out, if you transfer this t to the either side and take out the proportionality symbol, you need to introduce a constant. So that is known as a Wien's constant. I think it is, I'm not sure, it is 2900 odd. It is equal to 2900 odd something. Okay, meter Kelvin something. Okay, I'm not sure about it. Just from my understanding, I have just said that. Okay, fine. Kirchhoff's law. Kirchhoff's law is very important. It says, can anyone just read out, man? Nilesh? Nilesh Markle? Nilesh?
Yes, sir.
Kirchhoff's law, man.
Yes, sir.
Kirchhoff's law, can you just read it out?
Yes, sir. So it states that the emissivity of the body at a particular temperature is numerically equal to its absorptivity for radiant energy from body at the similar temperature.
So Kirchhoff's law is very simple. What it says is emissivity is equal to absorptivity. So he has just elaborated the things up. So me putting it in a shorter sentence, I can say the emissivity of a body is equal to the absorptivity at a particular temperature. So if the temperature is constant, the emissive power of a black body, to be precise, it is a black body, will be equal to its absorptive power. Okay, that is what it's Kirchhoff's law. So the law which is most useful for us for solving the problems is not Wien's law nor the Kirchhoff's law, but it is the Stephen Boltzmann's law. So the Stephen Boltzmann's law will help us to solve the numerous problems on the radiation. So let us see what it is. Can I call um, Rachan? Rachan Bhandari? Rachan? Can you just read out Stephen Boltzmann's law? Microphone not working. Pratish Suvarna?
The law states that the emissive power of a black body is directly proportional to
Proportional to the
fourth power of its absolute temperature.
very good. So Niharika, can you just repeat the same thing because this law is very important. It says the emissive power of a black body is directly proportional to the fourth power of its absolute temperature. That is the law. Please repeat it.
Um, the law states that the emissive power of a black body is directly proportional to the fourth power of its absolute temperature.
Project Rai,
Yes, sir.
same thing.
The law states that the emission power of a black body is directly proportional to fourth power of its absolute temperature.
Numan Saddi, Numan, not that. Shashank,
Yes, sir. Yes, sir.
Numan, you are
So,
there. So
yeah,
just read out the Stephen Boltzmann's law.
the law states that the emissive power of a black body is directly proportional to fourth power of its absolute temperature.
Right. So according to the statement given by all of you, you said that the emissive power of a black body is directly proportional to the fourth power of its absolute temperature, which I have written here. Okay. Now, when I take out this proportionality symbol and incorporate is equal to sign, when I try to equate the LHS and RHS, I need to put a constant. So that particular constant is known as the value of sigma. Sigma is nothing but the Stephen Boltzmann's constant. Do remember this value. He might give or he might not. So it's your responsibility to just remember this particular value. It is 5.67 into 10 to the power of minus 8 watt per meter square Kelvin to the power of 4. Okay. Rakshan Jain, what is the value of sigma?
5.67 into 10
7
to the power minus 8 watts per meter square per
Kelvin to
Kelvin
the power of
power of
4. Okay, good. Reza,
Yes, sir.
yes. What is the
Uh,
Stephen Boltzmann's constant?
5.67 into 10 raised to minus 8 watt per
Mhm.
meter square K raised to 4.
That's great. Okay, so remember these two values. That's more than enough in order to um, solve the problems. Okay, combined heat transfer. Few more problems are there, and one more class is enough. This particular module will be completed. Okay, again we shall have a revision. So hopefully your internals will start on the 20th, I guess, right? Information given regarding that, Ashwita.
No, sir.
Okay,
Sir, it's not
so
from
it's not from.
27th.
I don't know, man. So even HODs were discussing the same thing. It might start on 21st or 20th, but not sure.
I heard it's offline from 27th or something.
For the final years now.
Yes, sir.
Let's see. what they have planned. And offline, even I have heard it's only for the laboratories and not for the classes, even for the final years also. So, the exact outcome, hopefully, you can expect by today evening how it will work out. So, enjoyed your Diwali holidays, everyone?
Yes, sir.
Okay.
What about you, sir?
Yeah, mine was good. So, it was just in my hometown for all 3 days, having food, and I could sleep. That is my enjoyment for 3 days. Abdul Rahiman, Abhinav.
The present.
Yeah, sec. College is compulsory, but as per Ashwath Narayan, he said, if you read that notification, final years it's mandate, I guess. Not really much, no idea. So unless until the rule book is being released by our college, we cannot predict anything. Adarsh,
Present, sir.
Shanul, Ahmad Reza,
Present, sir.
Akshay Arkotia, Amit Yaslahari, Anmet Sirai, Ashwin K.
Sir Amrut.
Anmet Sirai is also there. Ashwin. Amrut is there. Ashwita,
Sir Ashwin, present.
Ashwin K. Ashwin K. Marked him. Ashwin and Anmet Sirai marked. Ashwita.
So she's gone for an interview.
Okay, today they had TCS, I guess, right? How many of you are attending TCS today?
I guess 5, 6 of them. No idea, sir.
Okay. All the best for all of them. Let them come up with the good results. Chandan C.
Present, sir.
Abhinoy.
Present, sir.
Had.
Yes, sir.
Python.
Yes, sir.
Kara.
Present, sir.
Gautam HS.
Yes, sir.
Javil.
Present, sir.
Karthik.
Present, sir.
Fazil.
Present, sir.
Ahmad Sihab.
Present, sir.
Ahmad Tausif Ali.
Present, sir.
Was. And Suraj.
Present, sir.
Afa. Namita Nair. Nandish.
Sir, Namita, present.
Okay, marked. Nandish. I think he had messaged me. Yes. Listen. Niharika.
Present, sir.
Nischit.
Present, sir.
George.
Present, sir.
Omkar. Ratan Jain.
Present, sir.
Suvarna.
Present, sir.
Rajat.
Present, sir.
Action King.
Present, sir.
Ramdas. Ranjat. Shabbat. Sagar S. Acharya. Shahzad.
Present, sir.
Shank PC.
Present, sir.
Shetty Sujay.
Present,
Present,
sir.
sir.
Tejas.
Present, sir.
Shravan Kumar.
Present, sir.
Sriraj. Saurabha, Sumant, Varun SL, Vigneshwara, Amit Sangol,
Present, sir.
Nilesh Markal,
Present, sir.
Hegde, Sandesh, Rachan, Rohan,
Present, sir.
Adarsh
Sir,
P.
Sandesh present, sir.
Yeah, Sandesh, Rohan, I marked you, man. Adarsh P. Muhammad Amin, Numan
Present.
Singh.
Present, sir.
Okay, guys, have a nice day ahead. I just left a few minutes early. Okay. Should meet up in the next class. Take care.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah.